All right, so what I'd like to do is kind of talk through the references. USD Ag Statistics, John had a bunch of them up there. I'll have a bunch of them up there. It's really good data, really good info. Having spent a lot of years at Crown CPM, I do have some pictures and some flow sheet stuff that kind of relate to their processes, so I want to give them credit for those. Also, the veg oil processing book, along with the Handbook of Soy Processing Utilization, these are really good reference materials for anybody that's looking for lots of technical detail and how things work and I'll call it the processes and the products and stuff that are used by a lot of oilseed processors and value add. I'm not going to spend a lot of time on this. John covered a lot of this, obviously, but basically that's just the basis process. There's lots of ways to kind of make the products, the meal, the oil, and things like that. Lots of different degumming systems. I'm not going to dive into those types of processes. I'm going off to the side where we're going into more the protein products and then the value-added veg oil products and stuff like that. So now, like John said, and I'll kind of reiterate, you look back 2009, you had about 3.3 billion bushels growing. You're up to about 4.4. So it's about a billion more bushels, but the crush hasn't even kept up. Its crushing is up by 660 million bushels. So there's plenty of feedstock for anything anybody wants to do in the US. You move on to the soy meal demand, and again, I'll reiterate some of what John said. The domestic growth is not as much as the export demand, and that export demand is going to be critical to continuing the growth of what's going to happen in the US. You have to get rid of the meal. It's a co-product. And you know the value economics will never work if you don't. So from the standpoint of, again, we're going to go after the protein value-added products now. Global soy food product markets from the FMI Future Market Insight, they're projecting a growth of 3.5%. From the standpoint of the global soybean meal market, that's being projected at approximately a 4.5% growth. Both of those things are good for the industry and create markets and stuff for all the products. So soy proteins. Basically what we're talking about is processed edible dry soybean products. We're talking, they're used in human, they're used in pet foods, milk replacers, aqua feeds, and then obviously there's other proteins, canola, sunflower, hemp, et cetera, that are kind of entering the market or in the market, but those are a very small fraction compared to soy. Soy is the big dog. It's got a vast majority of that market. So we'll concentrate on soy. Realize that as I go through these different processes, they're similar yet a little different because every feedstock has to be treated a little different. Because in the reality of it all, what you're doing is you're taking these oil seeds, you're breaking them into their components. And then you're either modifying those components or adding to things. So kind of keep that in mind as we go through. The flow sheets that you'll be seeing are fairly generic and simple. I did not put all the processes and all the steps in. I just tried to kind of highlight the big ones as we kind of go through. And again, some facilities will look a little different than others because they found ways they think to do things a little bit better. So first up is what we'll call the soy proteins, and this will be the flour and grit area. So as you take a look at this, you've got the whole soybean. You can literally just dehull, pull the fiber off, grind it up, make a full-fat soy flour or a full-fat grit, and you're at about a 20% oil, and you're at about a 40% protein type of a thing. You can go to the next level, and you can mechanical press, and you can pull out more oil. You get down to about 5 to 8% residual oil. Again, you grind it, you size it, and you can come up with your low-fat flour and grits. Or you go to the next level where now you solve and extract it. Once you solve and extract it, you're taking the oil down to less than 1%, and you have what's called a low-fat, or defatted, I should say, defatted flour and grit that can be made. That's the most common. That's what a majority of the folks utilize in the country and make. So there's also another twist to that in that depending on what the customer wants, you can actually add a little bit of fat back in, or you can add lecithin back in and make a refatted or lecithinated product type of thing. So those are some options that you have for what I will call upgrading and making some of those items. Now, what are some of the pathways that you need to do to actually be able to make some of these soy proteins and stuff? Because, again, it's all about functionality, and it's all about the product that you end up with. So you have to, it's not as simple as just making an animal feed out of meal type of thing. So as you go through that, there's kind of what I'll call two main pathways. One is via flash desolventizing system, and one is via a downdraft desolventizing system. And this happens right after the solvent extractor. And it's really about how you're taking those flakes and you're getting the solvent out without trying to damage the flake or without trying to toast it or reduce the protein levels and stuff in it. We'll start with the flash desolventizing. You'll see kind of an example in the picture off to the right. That's a traditional crown type flash desolventizing system. That one, I believe, is, I don't know, it's like 600, 800 ton a day. So it's obviously, it's several $1 million type process when you put it in. So to kind of walk through that process, you're taking the hexane-laden flakes. You're basically going through a long vapor tube where you're blowing it through. The solvent will vaporize out of the flake. You'll recover that solvent. The flake hits a cyclone, drops out. And then from there, you can go to a vacuum stripper, a dryer cooler, and now you have basically a solvent-free white flake that can now be utilized for further processing. Another option is doing what's called a downdraft desolventizing. It tends to be for lower capacities, but also it's a process that doesn't harm the flake as much, doesn't break it up. This is more of what I will call a tray style, low pressure steam, pulling a vacuum on it, and you're going through desolventizing again, recovering the solvent, and then you have your solvent-free white flake that can be used for further processing. I'd like to reiterate, both processes minimizes the reduction in PDI, and they also eliminate that toasted brown color that everybody sees when they see the meal. You don't want that toasted brown color in your food. Most people like the whiter color. They used to like whiter type flour, so everybody's shooting for that lower color. But also when you do that toasting at the higher temperatures, you're basically reducing what's called the PDI, and the protein dispersibility index. So in that particular case, it really comes down to functionality. So the processor does have the ability by how long and how hot they basically run it through those systems, which will bring down the PDI, because certain products, customers prefer the lower PDI, other products, they prefer the higher PDI. Now, as you look at the soy flour, really what you're doing is you're trying to get 97% approximately through a US 100 sieve. You're going through, you're doing a fine grinding system, you're going through a classifier, and you're creating that basic flour product that consumers are looking for. From the standpoint of the grits, really it's a coarser grind. You're getting through a number 8 or a number 80 sieve. You end up going through a roller mill, screener systems. Companies like CPM and stuff provide those types of products, or equipment, I should say. So now as we kind of take a look at the next one, soy protein concentrate. We're going another step further. We're basically taking now, and you're going to try to get to approximately a 62% minimum protein. You're going through, you got your hexane white flakes that came from those previous process. You're using a hydrous ethanol addition through another extraction step. Now, what Crown does, it's a different style extractor. They call it a Model 4 than what people are used to in the Loop Model 3 extractor. But it's kind of the same concept in that you're washing with ethanol, and you're going to basically recover that. What you're pulling out is mainly the carbohydrates, sugars type stuff in that process. So that co-product is the soy molasses. And then from there, your flake, if you want to call it that, continues on. You're going to go through a mechanical dewatering step. You're going to pull solvent off there. You're going to desolventize it. And then you're going to dry it and cool it. And you're going to have what's called a traditional soy protein concentrate. And again, in some cases, I'm kind of simplifying some of these things, but you kind of get the idea. From the standpoint of the different products and stuff, your food grade human consumption, you're talking infant formulas, dairy alternatives, meat alternatives, beverage powders, energy bars, and then the soy molasses is utilized for feed and moves into those types of areas for use. So now we'll talk protein concentrate for feed. So if you want to save some costs and you're only going to feed with it, you can actually take the meal from a traditional DT, which is from the traditional oilseed process. You do the same hydrous ethanol extraction. You're going through, you're pulling out the carbohydrates and stuff, creating that soy molasses. Again, you're doing the same process to desolventize it, recover it, and now you have that traditional soy protein concentrate, but it's a feed grade level as opposed to a food grade level. And for the feed grade, a lot of that really goes into replacements for fish meal, aquaculture, aquafeed type of stuff. It can also be used as one of your additives in livestock feed. Again, your higher protein concentration, which some people prefer in their rations. And then the soy molasses can get sold off as a feed additive. Soy protein isolates. Now this is the next level up. This is where you're going through a whole nother set of processes. You're getting rid of any of the remaining fiber, any of the remaining oil that you can get, and any of those remaining carbohydrates. You're trying to get yourself to a 90% crude protein minimum at that stage. Again, as you'll see as we talk through this, it's all about separation and or concentrating the different products as we go through. In this case, it's a little trickier. There's different companies have different ways to do this. This is kind of what I'll call a generic way of making it happen. But you're basically adding sodium hydroxide, or you're going through a centrifuge. You're pulling out that little bit of fiber. You're adding some hydrochloric acid. You're doing another centrifuge washing step. Then you ultimately spray dry it, and now you have your soy protein isolate powder. That is a very complicated process, which I very much simplified. And certain companies will have their own way of doing things. It's not a real common buy off the shelf type process like a traditional crush plant type of thing. Some of those products, basically, they're using tofu, soy milk, meat substitutes, extruded foods, and baked goods. So, that's kind of your high-end soy protein is the isolates. So to kind of summarize what I'll call the protein side of things, the demand for the veg oils, like was talked earlier and stuff, is being driven by biofuels. So now what processes are trying to figure out is how do we basically get rid of the meal? You really have three options. You export it, you drop your price so you can use it in more feed rations, or you try to expand more into the food market and specialty market. And there are a number of upgrades and expansions and call it new plants going in as relates to the soy protein concentrates and stuff kind of as we speak. Now we'll move on to the veg oil portion of it. So again, there's lots of different steps in the process. I just simplified it with what's there. I mean, there's literally 4 different ways to degum, whether you want to use acid degumming, water degumming. A lot is really dictated by what you're trying to do and if you're going to do some value-added products with it. So from a standpoint of the supply-demand for soy oil, again, it's been a fairly steady demand on the food side, the yellow bar. Back in 2009, we were about 14 billion pounds, and right now we're about 14 billion pounds. That really hasn't changed a lot. But obviously the quantity that is available has grown due to the crush going up, and then the biofuels have more than taken their fair share of it all. But there's also a little twist in that back, 7, 8, 9 years ago, they banned trans fats, which was created by partial hydrogenation of soybean oil. So that process got replaced. And when that happened, there was a reduction in the demand for soy oil into your margarines and different things like that. And that was kind of driven by that. So from the standpoint from the IMARC, their estimate is that you're going to see a growth rate of about 4.8% going forward from 2025 to 2033. Obviously, it is driven by a combination of food, Every time you have a new mouth to feed, you're going to have a little more demand there. But really, biofuels on a global basis is the bigger driver of that demand. So I'm going to talk about some of the value adds that can be done on, call it the liquid side, going through on the veg oils. And again, some of the veg oils this works well for, and other it doesn't. Each one has its constituents that we're trying to pull out, we're trying to modify, we're trying to do things with. But I'm going to try to just keep it fairly general and mainly to soy as I kind of walk through these. So from the standpoint of lecithin, you can create a liquid lecithin. In order to create a liquid lecithin, you got to start back, and you actually got to filter the crude oil as it's coming out of the crush plant to get rid of any potential little remaining fines. You don't want any of those meal fines in your lecithin product. From there, you have to do what's called a water degumming, where you add a little hydrogen peroxide to help with bleaching. You don't do your typical acid degumming. And so you are basically then pulling out the water-soluble phosphatides, and you can then take those after the degumming step and go through a thin film evaporator. Via the thin film evaporator, basically pulling off the moisture, so you have what's called a liquid lecithin that now can be sold, can be used as an emulsifier for chocolates, different food products, and stuff like that. You can also take that liquid lecithin and make it a solid. And so there's a couple plants that will do that around. Basically what you're doing is you're now reacting that liquid lecithin with acetone. You're pulling out the veg oil that's remaining in it. You're going through, you're going to distill off the acetone from the oil. You're going to recover that acetone, reuse it. The oil can go back into the refinery. The de-oiled lecithin is called, moves on, goes through a drying step. The acetone gets recovered and then put back, and now you can grind it, package it, and then you have what's called a solid de-oiled lecithin. And again, this can be used in baked goods, confectionery products, emulsifiers, things like that. Again, it's all about functionality. It's what the food company is looking for to be able to add into their products type of thing. They prefer a solid instead of a liquid. Another side slipstream coming off the process comes off the refining. So if you're doing what I'll call traditional caustic refining, you end up with a raw soap stock. A lot of people just put the raw soap stock right back in the meal. You also have the ability to upgrade that raw soap stock. You can react it with sulfuric acid. You're going to basically bring it down to about a 2 pH so that you can split the emulsion. The acid water gets neutralized and typically sent off to a city for further treatment, whereas the finished product coming out of that's called an acidulated soap stock. That can be used for like a feed additive. That can be used for road dust control. There are a few plants that refineries will send their soap stock to that do that. There are also a few refineries that do their own acidulated soap stock, depending if they want to go down that road. You can also take that acidulated soap stock and upgrade it. So you have this ability to basically run that through a distillation column. You're going to go through, heat it up, you're going to flash off the fatty acids, you're going to recover those fatty acids, and then you're going to end up with two products, what we call the black oil off the bottom, and then the fatty acid. The fatty acid can go into cosmetics, food, it can get blended back in with the lecithin if you want. So there's some good uses for the fatty acids. The black oil, again, feed additive or even road dust control, we've seen it used for over the years. So now you've got distillate. And distillate is what comes off of the deodorization, which is the final step that you do in a veg oil refining. The whole premise behind deodorization is you're heating it up to about 500 degrees. You're stripping off any remaining color bodies, flavors, any of the minor constituents, so that you have that odorless, tasteless salad oil that you see on the shelf type of a thing. So that co-product, if you want to call it that, is about 0.1%. Is all you're getting out of it, but it's significantly more valuable than the oil itself, and it has a lot of value add to it. So what's it made up of? It's made up of tocopherols, tocotrienols, sterols, fatty acids, and then some other minor components. Basically, you're going through and you've got those natural antioxidants that you ultimately want to separate and make into the subcomponents. It's actually the largest source of natural vitamin E that's in the world. It's really kind of interesting. A lot of people don't understand what really value is in those distillates and kind of what they go for. The distillate is typically sold off to like a pharmaceutical or food company for further processing. There's some of called the majors that will actually take that and bring it to a central place and then do it themselves. But it's really a lot of different distillation steps that you're doing. And you're trying to get those fine cuts to concentrate those individual components to bring the value there. And then it's sold off into what I'll call the industry, food industry for, you know, the vitamin E, the specialty chemicals, and then as antioxidants and food ingredients. And, you know, you can make little capsules out of it. But again, there's a lot of value in that stream. The next one is hydrogenation. Again, it was very common up until trans fats kind of knocked it out, but it's still there. It still happens, but it's actually being used now to make candles or crayons. And so it's basically what you're doing is taking a nickel catalyst and you're reacting the soybean oil or veg oil with hydrogen, breaking the double bonds, creating a harder product. So you're creating a new melting point is basically what you're doing. And so you get to go through, you got to filter out the nickel catalyst, you bring that around, that gets sold back typically for recycling to the nickel supplier type of thing, and you end up with a hydrogenated product. So again, not nearly as often as it used anymore, but it does have its role in what we'll call the industrial uses or other non-food uses. With the removal of partial hydrogenation of soybean oil really kind of brought about then the push for inner esterification. And there's kind of a couple different ways to do inner esterification. You've got your low melting point veg oils that you kind of bring together, and you go through, you add a catalyst, you're agitating, you're going through a centrifuge, you're washing it, you're bleaching it, you're filtering out the clay, you're going to deodorization. The whole goal, again, is to create a different melting point, mouthfeel type product by going through and blending in the different oils and running your reactions and stuff. So again, it's margarines, it's food additive feedstocks. Those are the different things that the inner esterified products will go to. Next one is enzyme esterification. A little simpler. You're using the deodorized oil in this case. You're reacting with this enzyme, and you're coming out with your inner esterified product. Again, it's all about the mouthfeel. It's about the functionality. It goes into margins and stuff, but it's another avenue to get to the types of products that the food companies are looking for. Winterization, it's kind of for sunflower oil and corn oil, it's really what you're doing is you're dewaxing. You're cooling it down. You're finding that point where it crystallizes. You got to give it some time in a crystallizer. You're going through that holding tank. You're filtering out the waxes, and then it continues on, and now you have what's called a dewaxed sunflower oil or corn oil. This makes it so it's not cloudy on the shelf as a salad oil. Goes into food products. It doesn't poison the catalyst when it goes on to being used for biofuels and stuff. So it almost is kind of a base step to a certain extent. I wouldn't call it a true value add process, but it's a necessary process. Fractionation is another way of basically taking a palm oil, for example, and light dewaxing, you're cooling it down, you're creating crystals that then you can filter out, and it's really all about creating different liquid characteristics from the one feedstock. And so you can take the inner esterified oil, you can take a palm oil, and then you can do those steps. And that, again, it's all about meeting the food product specs for melting points, functionality. Those are the types of things you're trying to pull off when you're doing that. So now let's kind of go into more of the biofuels part. And like you kind of heard earlier, if you're in the earlier one, You go back to 2009, it was barely anything. It was a little over 1.6 billion pounds. You go prior to that, it was almost nothing. That was kind of that first wave in 6, 7, and 8, where the US gave subsidies and you had your traditional biodiesel plants were being built by farmer co-ops, or some of the ag guys put some biodiesel facilities next to theirs. Since then, in the last 10 plus years, renewable diesel has really kind of taken the forefront, and now SAF type of thing is so that approximately half is being of the soy oils going there. And like I said, there's a lot of other feedstocks, whether it's tallow, used cooking oil, anything they can find that has a good carbon chain to play with, they'll take it. So let's talk about the traditional biodiesel process. In this particular case, I'm kind of mimicking the Crown one. They use what's called decanters in their process. There are other companies, Westphalia, different ones like that will use a centrifuge-based process. Again, it's all about separation. So you're taking that pre-treated veg oil, and I think it's critical to understand what pre-treated veg oil is. Basically, it's your typical refining, taking all the way through typically to the bleaching step, so that you've taken out the calcium, magnesium, and phosphorus so that you don't have the poisons to the catalyst. So you have to have that pre-treatment step to get then to be able to go to the next step, which is reacting call it bleached oil, with methanol and a catalyst, so that you end up with your methyl ester, and that's really what you're creating. You decant it off, you water wash it, you recover the methanol, you go through, you filter it, and you have then a traditional 100% biodiesel that has been kind of the stable for many, many years until the renewable diesel came up. The reality is, Henry Ford did this back in, I think, like the 1920s. It's not a new process. It was not revolutionary, but it's amazing kind of how it really kind of changed here over the last 20 years. One of the byproducts of that process is glycerin. So if you're taking, say, 100 gallons of veg oil into your typical biodiesel plant, you're going to end up with about 94 gallons, give or take, of methyl ester biodiesel, and you're going to have about 6 gallons of crude glycerin. Now you got to do something with the crude glycerin. So you can go through a process that basically you go through a crude still, you're heating it up, you're stripping out the glycerin from what's called the foots, or it's really mainly salts and stuff. That bottom foot, you do a last thin film evaporation, recover any of the remaining glycerin. That glycerin then, you go through a deodorization step, you go through a bleaching step, and now you have what's called USP grade glycerin. It can be used in cosmetics, moisturizers, laxatives, things like that. So it's really a nice value add for the traditional biodiesel guys. Next one up is what we'll call renewable diesel. So again, this is the push by the petroleum guys to get into the game. So a little history, back when biodiesel originally started, the petroleum boys were against it, okay? They fought it tooth and nail. The subsidies were in place for a few years, and then they got pulled, and the whole industry suffered back in the mid-2000s. Now, the petroleum boys are on board. And I should say, one of the biggest reasons they also fought it was, they obviously didn't want that in the marketplace, but the logistics of handling 100% biofuels was painful for them, because they do everything in these huge tanks, pipelines, et cetera, and it was just a pain. With renewable diesel, it really changed the game for them, because they can really integrate it into their facilities with not a whole lot of hassle, but it's not cheap either. So basically, as it relates to the renewable diesel, you take a veg oil, it can be tallow, it can be used cooking oil, but you go through, if it's not already pre-treated from a crush plant, so they can bring in what I'll call the bleached oil or the deodorized oil and run it right into their hydro processes. Or a lot of them have actually installed pre-treatment systems at their site, so they can buy the different feedstocks, clean it up, and then send it on. The biggest thing with the petroleum guys, they're doing a hydro processing trick. They're using catalyst beds, and by manipulating what's going on, by adding the hydrogen, They're pulling off the oxygen, and they're trying to make molecules that basically resemble typical diesel, so that they can meet the ASTM specs. So you got to meet the specs. And so as such, you end up with this split that you get about a 90% yield when you're making renewable diesel going through that process step. And you end up with some of these co-products that are like naphtha, SAF, and like gasoline splits, which then they kind of utilize, blend off, and deal with. But that's kind of the renewable diesel step. When you go to the sustainable aviation fuel, you're actually taking that renewable diesel and going through more catalyst beds and more isomerization, hydroprocessing, and now you're actually creating your SAF, but about half of that goes to SAF, then the rest goes back and stays as like a renewable diesel or a naphtha and things like that. So it's an interesting dynamic that depending on the subsidies, depending on, call it the splits and what they're trying to do, the petroleum boys can basically modify the carbon chains of the vegetable oil to create this sustainable aviation fuel and to create the renewable diesel. And it's all done in similar process vessels, but it's like $1 billion process here. This is not the faint of heart. This is not stuff that you will typically see at a veg oil plant type of a thing. And so it's really just kind of getting started. We're on the cusp of it. I think there's like 2 billion gallons of SAF that are kind of possible to be kind of made right now. And there's like 100 billion gallon market for it. You can take every veg oil and every youth cooking oil and every tallow in the whole freaking world and you won't have enough. So it's really an interesting dynamic as it relates to that. So, you know, you've got an unlimited demand as it relates to that aspect for the veg oils and stuff. But it's interesting how they're now also starting to look at carbon scores, and they're looking at all these other things to drive the subsidy. This doesn't make economic sense. Let's face it, if it wasn't for the subsidies and stuff, it wouldn't be happening. And so we're actually working with one company on a project, and they got the Biden administration to give the blessing for their DOE loan back guarantee stuff back in the beginning of January. The end of January, they're supposed to get their first tranche of money. The Trump administration put that on hold for review, and literally just this last week, they got final blessing approval. So that was good news, because I think a lot of people out there are wondering what's going to happen to sustainable aviation fuel, renewable diesel with the new administration and stuff. And it tends to be, at least for past history, things that are what I'll call ag-based or farmer-based, ethanol, different things like that. The Republicans tend to let it go. They don't really push it hard and fast, where the Democrats have been pushing it hard and fast. So the Trump administration, all bets are off on stuff, but that was the first sign that they were willing to let this project continue through with its backing and funding of the government. So that's a good sign, if you want to call it that, for the egg industry and for those types of projects. Now, there's another one that's ethanol-based, because SAF can also be made by upgraded ethanol. So you can take that ethanol and upgrade it to an SAF. There's another one that's sitting out there that's still waiting for the Trump administration to bless off. So it'll be interesting to see where they draw the line, what they support, and things like that for all these types of things. Again, to summarize, there's unlimited demand for veg oils into the renewable fuels area, and it will be that way for a long time. Government policy, government subsidies will decide and change that. Probably half the subsidies are actually state-based, so the blue states on the coast, California, well now Minnesota, Illinois, et cetera. About half of the, call it subsidies, are coming from them. The other half's coming from the federal governments and their different programs and stuff. So it's a very, call it, dynamic industry right now in the renewable fuels and stuff. There's a lot going on. Stay tuned to a certain extent to see how everything ends up working out and going. But again, it's an unlimited demand. If you can figure out how to get rid of the meal, you can process a whole lot of soybeans to make the oil. but you're ultimately going to have to get rid of the meal. All right, so with that, I think I'll call it good, and I'll take questions. Yes, back there.
Concerning the SAF.
Yes.
Is there anything in the technology aspect of development that may reduce that production cost?
I would think some. It's like anything. There's companies like UOP, Honeywell. They're really the petrochem companies that have developed the technology, and it's catalysts, and it's what they do with it. So yeah, I would say there's definitely potential for that, because like I said, you go through and you want to create a facility that can do 100 million gallons of SAF. You're talking a lot of money. You're talking hundreds of millions up to $1 billion type of thing. But it's really going to fall back to what I will call the petrochem guys to develop that and push that and make it happen. And that's really the world we're living in. It's great because we're the feedstock for a lot of that stuff from a standpoint of the ag industry. And let's face it, there's also going to be cellulosic ethanol that ultimately can get upgraded into SAF and traditional ethanol. But you also can't forget, you also have the renewable diesel side that is for trains and ships and everything else, trucks. So you tend to rob Peter to pay Paul when it comes to SAF, because you're actually, instead of making renewable diesel, you're making SAF. Because it's a very similar process, just further going down the chain, trying to create what we'll call the lighter cuts of the carbon chain so that you have that aviation fuel. Because again, it's a different spec, different thing that you're trying to meet. But it's not cheap. It's not cheap, and let's face it, veg oils went from, say, 30 cents a pound to 60 cents a pound when the renewable diesel thing kicked in. And so even at that point, it's still, they need, I don't know, $3, $4 a gallon subsidy to make it work. So you got to have $200 a barrel petroleum before you start having the economics work out. So I don't know, it'll be interesting. It's a global thing. Europe is ahead of the US. That's the other thing that most people don't realize is Europe really is ahead of the US in the renewable diesel technology and in the SAF technology. And to a certain extent, we've been adapting a lot of what they've already started doing, type of thing. But yeah, there's Topso, UOP, Honeywell, there's a few others out there, LanzaTech, that are doing a lot of stuff in these areas that it's kind of exciting. It is interesting. Carbon capture off of these ethanol plants has turned into a big thing and things like that. But for what I'll call the traditional oil seeds and stuff, canola, the high content oilseed canola, 40%, you're seeing that big demand. I mean, you're almost doubling the crush capacity in canola in Canada because of that oil. And they want the oil, and Canada has all these SAF renewable diesel subsidies going on too. But guess what? You only got 60% that you got to get rid of in the meal, as opposed to soy that's got to get rid of 80. So the high oilseed contents, rapeseed, canola, tend to have a little advantage right now, but they're not as prevalent. They're not as big as it relates to what's available out there. Any other questions? All right, well, I appreciate your time. Thank you.